In mathematics, E6 is the name of some closely related Lie groups, linear algebraic groups or their Lie algebras, all of which have dimension 78. The same notation E6 is used for the corresponding root lattice, which has rank 6. The designation E6 comes from the Cartan killing classification of the complex simple Lie algebras. This classifies Lie algebras into 4 infinite series labeled N, Bn, Cn, Dn, and 5 exceptional cases labeled E6, E7, E8, F4, and G2. The E6 algebra is thus one of the 5 exceptional cases. The fundamental group of the complex form, compact real form, or any algebraic version of E6 is the cyclic group Z, 3Z, and its outer automorphism group is the cyclic group Z, 2Z. Its fundamental representation is 27-dimensional, and a basis is given by the 27 lines on a cubic surface. The dual representation, which is an equivalent, is also 27-dimensional. In particle physics, E6 plays a role in some ground-unified theories, real and complex forms. There is a unique complex Lie algebra of type E6, corresponding to a complex group of complex dimension 78. The complex adjoint Lie group E6 of complex dimension 78 can be considered as a simple real Lie group of real dimension 156. This has fundamental group Z, 3Z, has maximal compact subgroup the compact form of E6, and has an outer automorphism group non-cyclic of order 4 generated by complex conjugation and by the outer automorphism which already exists as a complex automorphism, as well as the complex Lie group of type E6. There are 5 real forms of the Lie algebra, and correspondingly 5 real forms of the group with trivial center, all of real dimension 78, as follows. The compact form, which has fundamental group Z, 3Z and outer automorphism group Z, 2Z. The split form, EI, which has maximal compact subgroup SP, fundamental group of order 2 and outer automorphism group of order 2. The quasi-split form EII, which has maximal compact subgroup SU times SU, fundamental group cyclic of order 6 and outer automorphism group of order 2. EIII, which has maximal compact subgroup SO times spin, fundamental group Z and trivial outer automorphism group. EIV, which has maximal compact subgroup F4, trivial fundamental group cyclic and outer automorphism group of order 2. The EEIV form of E6 is the group of collineations of the octonionic projective plane OP2. It is also the group of determinant-preserving linear transformations of the exceptional Jordan algebra. The exceptional Jordan algebra is 27-dimensional, which explains why the compact real form of E6 has a 27-dimensional complex representation. The compact real form of E6 is the isometry group of a 32-dimensional Riemannian manifold known as the bioctonionic projective plane. Similar constructions for E7 and E8 are known as the Rosenfeld projective planes, and are part of the Freudenthal magic square. E6 is an algebraic group. By means of a Chevalier basis for the Lie algebra, one can define E6 as a linear algebraic group over the integers and, consequently, over any commutative ring and in particular over any field. This defines the so-called split adjoint form of E6. Over an algebraically closed field, this and its triple cover are the only forms. However, over other fields, there are often many other forms, or twists, of E6, which are classified in the general framework of Galois cohomology by the set H1, which, because the Dynkin diagram of E6 has automorphism group Z, 2Z, maps to H1 equals hom Z, 2Z, with kernel H1, over the field of real numbers. The real component of the identity of these algebraically twisted forms of E6 coincide with the three real Lie groups mentioned above, but with a subtlety concerning the fundamental group. All adjoint forms of E6 have fundamental group Z, 3Z in the sense of algebraic geometry, with Galois action as on the third roots of unity. This means that they admit exactly one triple cover. The further non-compact real Lie group forms of E6 are therefore not algebraic and admit no faithful finite-dimensional representations. The compact real form of E6 as well as the non-compact forms EI equals E6 and EIV equals E6 are said to be inner or of type 1 E6, meaning that their class lies in H1, or that complex conjugation induces the trivial automorphism on the Dynkin diagram, whereas the other two real forms are said to be outer or of type 2 E6. Over finite fields, the Lang-Steinberg theorem implies that H1 equals 0, meaning that E6 has exactly one twisted form, known as 2E6. See below. Algebra. Dynkin diagram. The Dynkin diagram for E6 is given by, which may also be drawn as or, roots of E6 although they span a six-dimensional space. It is much more symmetrical to consider them as vectors in a six-dimensional subspace of a nine-dimensional space. All 27 combinations of where is one of all 27 combinations of where is one of simple roots. An alternative description. An alternative description of the root system, which is useful in considering E6 times SU as a subgroup of V8, is the following. All permutations of preserving the zero at the last entry, and all of the following roots with an odd number of plus signs. Thus the 78 generators consist of the following subalgebras. A 45-dimensional SO subalgebra, including the above generators plus the 5 Cartan generators corresponding to the first 5 entries. Two 16-dimensional subalgebras that transform as a WEYL spin or of and its complex conjugate. These have a non-zero last entry. One generator which is their chirality generator, and is the sixth Cartan generator. One choice of simple roots for E6 is given by the rows of the following matrix, indexed in the order WEYL group. The WEYL group of E6 is of order 51840. It is the automorphism group of the unique, simple group of order 25920, PS omega 6 minus, PSP4 or PS omega 5. Cartan matrix. Important subalgebras and representations. The Lie algebra E6 has an F4 subalgebra, which is the fixed subalgebra of an outer automorphism, and an SU times SU times SU subalgebra. Other maximal subalgebras which have an importance in physics and can be read off the Dynkin diagram, are the algebras of SO times U and SU times SU. In addition to the 78-dimensional adjoint representation, there are two dual 27-dimensional vector representations. The dimensions of the smallest irreducible representations are 1, 27, 78, 351,650, 1728, 2430, 2925, 3003, 5824, 7371, 7722, 17550, 19,305, 34,398, 34,749, 43,758, 46,332, 51,975, 54,054, 61,425, 70,070. 78,975, 85,293, 100,386, 105,600, 112,320, 146,432, 252,252, 314,496, 359,424, 371,800, 386,100, 393,822, 412,776. 442,442. The underlined terms in the sequence above are the dimensions of those irreducible representations possessed by the adjoint form of E6, whereas the full sequence gives the dimensions of the irreducible representations of the simply connected form of E6. The symmetry of the Dynkin diagram of E6 explains why many dimensions occur twice, the corresponding representations being related by the non-trivial outer automorphism. However, there are sometimes even more representations than this, such as 4 of dimension 351, 2 of which are fundamental and 2 of which are not. The fundamental representations have dimensions 27, 351, 2925, 351, 27, and 78. E6 polytope. The E6 polytope is the convex hull of the roots of E6. It therefore exists in 6 dimensions. Its symmetry group contains the Coxeter group for E6 as an index 2 subgroup. Chevalier and Steinberg groups of type E6 and 2E6. The groups of type E6 over arbitrary fields were introduced by Dixon. The points over a finite field with Q elements of the algebraic group E6, whether of the adjoint or simply connected form, give a finite Chevalier group. This is closely connected to the group written E6, however there is ambiguity in this notation, which can stand for several things. The finite group consisting of the points over FQ of the simply connected form of E6 or more rarely and is known as the universal Chevalier group of type E6 over FQ. The finite group consisting of the points over FQ of the adjoint form of E6 and is known as the adjoint Chevalier group of type E6 over FQ, or the finite group which is the image of the natural map from the former to the latter. This is what will be denoted by E6 in the following, as is most common in texts dealing with finite groups. From the finite group perspective, the relation between these 3 groups, which is quite analogous to that between SL, PGL and PSL, can be summarized as follows. E6 is simple for any Q, E6, SC is its Schur cover, and E6, AD lies in its automorphism group. Furthermore, when Q-1 is not divisible by 3, all 3 coincide, and otherwise, the Schur multiplier of E6 is 3 and E6 is of index 3 in E6, AD. Which explains why E6, SC and E6, AD are often written as 3E6 and E6-3. From the algebraic group perspective, it is less common for E6 to refer to the finite simple group, because the latter is not in a natural way the set of points of an algebraic group over FQ, unlike E6, SC and E6, AD. Beyond this split form of E6, there is also one other form of E6 over the finite field FQ, known as 2E6, which is obtained by twisting by the non-trivial automorphism of the Dynkin diagram of E6. Concretely, 2E6, which is known as a Steinberg group, can be seen as the subgroup of E6 fixed by the composition of the non-trivial diagram automorphism and the non-trivial field automorphism of FQ2. Twisting does not change the fact that the algebraic fundamental group of 2E6, AD is Z, 3Z. But it does change those Q for which the covering of 2E6, AD by 2E6, SC is non-trivial on the FQ points. Precisely. 2e6. Scoring is a covering of 2e6, and 2e6 add lies in its automorphism group when q plus 1 is not divisible by 3, all three coincide, and otherwise. The degree of 2e6 SC over 2e6 is 3 and 2e6 is of index 3 and 2e6 add, which explains why 2e6 SC and 2e6 add are often written as 3 2e6 and 2e6 3. Two notational issues should be raised concerning the groups 2e6. One is that this is sometimes written 2e6, a notation which has the advantage of transposing more easily to the Suzukian Re groups, but the disadvantage of deviating from the notation for the FQ points of an algebraic group. Another is that whereas 2e6 SC and 2e6 add are the FQ points of an algebraic group, the group in question also depends on Q and E6 add. The groups E6 and 2e6 are simple for any Q, and constitute two of the infinite families in the classification of finite simple groups. Their order is given by the following formula. The order of E6, SC or E6 add can be obtained by removing the dividing factor GCD from the first formula, and the order of 2e6, SC or 2e6 add can be obtained by removing the dividing factor GCD from the second. The Shor multiplier of E6 is always GCD as its Shor cover. The Shor multiplier of 2e6 is GCD as its Shor cover, outside of the exceptional case Q equals 2 where it is 22-3. The outer automorphism group of E6 is the product of the diagonal automorphism group Z, GCDZ, the group Z2Z of diagram automorphisms, and the group of field automorphisms. The outer automorphism group of 2e6 is the product of the diagonal automorphism group Z, GCDZ, and the group of field automorphisms. Importance in physics. N equals 8 supergravity in 5 dimensions, which is a dimensional reduction from 11-dimensional supergravity, admits an E6 bosonic global symmetry and an SP bosonic local symmetry. The fermions are in representations of SP, the gauge fields are in a representation of E6, and the scalars are in a representation of both. Physical states are in representations of the coset E6, SP. In ground unification theories, E6 appears as a possible gauge group which, after its breaking, gives rise to the SU times U gauge group of the Standard Model. One way of achieving this is through breaking to SO times U. The adjoint 78 representation breaks, as explained above, into an adjoint 45 spin or 16 and as well as a singlet of the SO subalgebra, including the U charge we have where the subscript denotes the U charge.